Okay, so let's just very quickly finish the last week's lecture. So we were almost at the end. So somewhere here, just comment. And I assume you can hear me. Otherwise, I would be delivering some messages. By the way, so feel free to interrupt me at any time with questions, and I will stop, or I'll try to stop as frequent as often as I can to just make sure that you can ask questions. So okay, so last time what we were doing is we were like discussing the work and exec couple of system calls, and I just wanted to make sure that we finish it and we all understand what's going on there. So the idea here is the following. So we started with those motivating examples, like where you use small utilities from existing ecosystem and essentially combine them in some kind of a flavor of a programming language, which shell implements with those pipes and IO redirection. And in this specific example, what we do is that we cat the ls.c file, pipe it into the grep, which filters out the string which contain main, which and then we word count them. And someone last time after the lecture, one of the students stopped by and asked, okay, is it really that useful? So like what I'm trying to explain. So do we really often run those pipes or pipelines in our daily lives? And I was trying to like show that person a couple of examples from I have a list of useful commands which I try to remember and just remember the syntax. But what I wanted to say is that since Tuesday, I was working on a paper and I used those commands. So the reason for that was something like, LaTeX, which I use for writing and building PDFs, says, okay, there is an error in such and such line, but I don't know the file. So, and I ran something similar to this where I did grab of everything, like I was error, whatever. Didn't greatly, it was if else. It had like two E's. I typed two E's minus R in my current folder. R stands for descent into subfolders. And then I did something like, and I didn't pipe anything, but essentially I just wanted to make sure that it will list me all the files where this line, which I was looking for, was located. So what I'm arguing right now is that shell is still a powerful tool today, despite the fact that it's been almost 50 years, more than 50 years, because in early 70s we started working with Unix systems. So yeah, I believe that it was a good design choice. So like people are using this. Okay, so but back to this example. So what is it we're doing here? Like if either you were to implement a shell, and we talked about it last time, or you building a program in which you just execute something and want the result back, meaning that this WC minus L can either pipe back to your program, or you want to just simply redirect it into some kind of a file foobar. How the code should look to build those pipelines, right? So and at high level, what you're doing here is you first create a pipe. We didn't discuss it, a system call which does it, but I'll show it in a second. The pipe really creates a buffer inside the kernel, and it returns you two file descriptors. So, and you can then do something with those file descriptors. So if you forking here, you're passing those file descriptors to your children, and you can start manipulating them. So for example, if you want to connect to programs like P1 with a pipe into P2, then you essentially close the standard output for this program and like making like there's another system call which is called duplicate, and duplicate a pipe into this file descriptor, which is standard output. And you do for this program too, you standard you close the standard input and duplicate a pipe. And then you close, like essentially, if you have a pipe here and you might accidentally, because you were doing something with file descriptors, so this little thing is a pipe. If you were doing something with them, just make sure that you correctly close the ends of the pipe, because otherwise the program which will be running here later on, like whatever it is, like WC, for example, might get confused and will be waiting for input for an infinite amount of time. So I'll explain it in a second. But essentially what you do after you manipulated the file descriptors, you say, look, at this point, I will exec into whatever the program I want to run. Let's assume it's cat. And I will exec here into WC and like to create a pipe, which is something like cat of something into WC, right? So let's take a look at a concrete example. So this is a piece of code which works in x86 and most likely works on Linux as well. So essentially what we're doing, we word count on the read end of the pipe. So what we do here is we say, look, we'll first create a pipe, and the system call pipe takes an argument to an array of 2 elements, right? This is P. And essentially the idea is that this is how you, in C, if you want to write something like you want to return a tuple with 2 file descriptors, fd1 and fd2, you really cannot in C, right? Because there is no such syntax. And instead, what you do is you say, there is a pipe, and I will pass an array containing this 2 as an argument here, right? And what will happen is that the pipe will fill in those ends of P. At this point, you say, I'm going to be forking because I will be running 2 children. So if I'm inside the child, meaning that fork returns 0 here, actually do some very minimal error checking here. I will close my standard input, right? So I'm inside the child. I will duplicate this file descriptor P, which was returned here as element 0. And essentially what it does is that it will put this, if you have an array of P, which contains 2 file descriptors, fd1, or let's say fd0 and fd1, then this fd1 will be duplicated into the recently closed 0, because it's the most, the file descriptor, the closed file descriptor with the least significant number, right? And after that, you say, look, since I'm not gonna no longer use those ends of a file descriptor, right? Because at this point, if this is your file descriptor table and you have a pipe and a kernel, so this is a pipe, you have 2 file descriptors which were returned by P2, and they kind of point, one points to the right end of a pipe, another points to the read end of the pipe. And you essentially said, okay, I will connect my standard input to the read end of the pipe. So apparently I have to flip those to make this example correct. And what you're doing here with those close methods, you're essentially making sure that these 2 are closed, right? And after that, you essentially exec into WC, right? So the end result of it is that if you're running in a kernel in a parent in this line 13, and you're doing write into the right end of the pipe. So let me just quickly erase everything quick to make sure that we have space. So the result of it will be something that we have 2 processes, right? So like inside the parent, we have a file descriptor which has 2 ends of a pipe. This is like P0 and this is P1. And essentially P1 is pointing to the right end of a pipe in a kernel. And P0 points obviously here. And inside the child, our file descriptor table will look like something like file descriptor 0 will point to this end of the pipe. And these are 2 different processes. So this is the parent, which we were running, this our main, which we were running here. And the child, after we exec into it, so the child is WC, right? And so if we essentially write inside the parent, we write into P1, we'll write hello world. into this end of the pipe, right, into the right end of the pipe, and the child will just happily read it, right? And the moment we close both file descriptors in a parent, so essentially closing those two links, the WC, remember the WC, I never showed the code, but it will realize that the pipe, the right end of all the right ends of the pipe are closed because we closed them here as well. So there is nothing pointing into this pipe. There's nothing like that anymore. And it's time to exit. And essentially word count will print out whatever it has, like standard output. It will print out 2 on the console, just because there will be like 2 words or whatever the output of WC is. Are there any questions about this example? And this is kind of the skeleton of what you will be doing when you will be working on your first homework assignment, which is a cell. So essentially, the cell itself will require you to implement like full support for like parsing the command prompts, kind of like saying, okay, I know that whatever cat of ls.c, and the user wants me to pipe it into WC minus L, for example, right? So we'll provide some infrastructure which will do the parsing, like kind of returning it to you as a list of tokens, but you will have to like essentially fork the children, connect everything with pipes, stuff like that. And that's the first homework assignment, which will be assigned today or tomorrow. Any questions about it? Question on the chat. Is closing P0 and P1 necessary? Yes. So the reason is following. So let me change the color real quick here to highlight the problem. Maybe the green is better color. Okay, blue is good enough. So if you suddenly don't close, for example, these ends of the pipe, right? So, and after you forked, so essentially, when you open the pipe inside the parent, it created something like P0 and P1 ends of the pipe, and they point to P0 points to the read end of the pipe, right? And P1 points to the right end of the pipe, right? And just for the sake of example, you use this P1 here to write into the pipe from the parent, and you put this hello world. WC will run some kind of a loop, which will be kind of like, I will be reading from my standard input, which is 0, and into a buffer and some len of a buffer here, right? And it will be returning some error here, like some result. And so what happens is that unless you close these 2 ends of the pipe, for the first invocation, you will happily read hello world. But for the second invocation, you will stuck here forever in this read, right? Why is that? Because the read is implemented in such a manner that it will block, like the pipe will be empty because you already read hello world, as long as you provide the buffer, which is larger than hello world string, right? But since you're saying, okay, you're trying to read again, and there are some right ends of the pipe are still open, the implementation of a pipe internally, and we'll take a look at it later in the class, will say, look, I'm going to be waiting because there is a chance someone will later write it, like you will be reading here, right? So it's critical to close these 2 to make sure, and these 2 to make sure that all the right ends of the pipe are closed. And so this read, when you invoke it next time, returns 0 here. Yeah, it returns 0, which means that the read pipe ends of the right ends of the pipe are closed, and you can like essentially exit the program saying, okay, there will be no more input in the pipe, I'm done running. And I will answer the question in a second, I see hands. But what I wanted to say, the reason it's done this way, let me again erase, I'm just trying to figure out the space somewhere here. Like this is our example, but what I wanted to show you, imagine when you're writing here, instead of like hello world, you do like either something very, very large on just, or just for example, you do a cat of a very large file. And you grab it into, or maybe you potentially WC it, and you're searching for some substring foobar. And imagine that this very large file is like a megabyte or gigabyte, right? When the cat, which implements the write into the pipe, it will only be able to write as much as there is space in a pipe, like in x86 is 512 bytes. And then it exits, and essentially the implementation of a cat that it will be trying to write again. And the next write, if the pipe is full, will be blocked here. But these two processes, cat and grab, they will be running concurrently. Remember my story. So like cat runs for a while, switches into the kernel switches back into like chooses the next process to run, and this runs WC. At this point, this whatever we're running here, WC reads something from a pipe, clearing it, right? So like the pipe will be like, will have 0 bytes. It will process the input and will, in some infinite loop, drop again to read something from a pipe. Since the pipe is empty, we will switch back. So here, we'll switch back into the kernel. The kernel will switch back to the cat program. The cat program will start running, write something more into the file, into the pipe. Maybe again, since the file is large, it will write again the same 512 bytes into the pipe, which is in the kernel. And the kernel like says, okay, the pipe is blocked, so I will context switch back into WC. And these two programs will be running for some time, right, to process the input, right? So they are, imagine if you're running on a single CPU, the operating system will be context switching between them. But eventually, when the program on the left side of a pipe will reach the end of this very large file, it will say, okay, I'm done writing, like, and it will close all the right ends of the pipe and will exit. The pipe will still remain in a kernel for a little bit, because the kernel implements reference counting, and as long as there is a single reference, it will let WC read everything from a pipe. But after that, WC says, okay, I'm done, and I'm exiting as well, right? So hopefully this is clear. So it took me a little longer, but just to make sure that we understand how it runs. So like, because later in a shell, every year I see implementations which try to write everything in a pipe and exit, but it's sometimes impossible because, and only after that, run the second end of the pipe. You cannot, because it's possible when you're writing something which is less than 512 bytes on x86 or some number on Linux. But the moment you're trying to write something larger, you will not be able to do it in a single iteration. You will need to like make sure that you create two processes and they will run for some time, interleaving on the operating system kernel. So I see that Ali has a hand. Let me just quickly, not here. Okay, Ali, do you have a question I can answer?
Yep. So my question is, usually in C language, like if a reader is reading something, it could be either file or a string. There's
Yeah.
always end of string, like a null character at the end of
Yeah,
string.
yeah.
How does child process know that like the contents in a pipe is finished? I don't need to read anymore.
All right. So at the level of the operating system kernel, the kernel which implements the pipe, and I promise was 90% probability that we're gonna reach like, and we will read through the implementation of a pipe in x86, and other operating systems implement pipes similarly. What happens is that, let me erase everything on this slide. What happens is that the operating system, when it looks at this string, it doesn't care what it is. It can be any garbage. It can have a different symbol, no null pointer, like here will be another null here, right? Because if you count the bytes, it's 1, 2, 3, 4, 5, 6 for the space, 7, 8, 9, 10, 11, 12. I missed, where's my 0? I would assume this, like, am I counting it correctly? So the idea which I wanted to kind of promote is that you have to like write an extra character here, but essentially at the level of the operating system, it doesn't care. It just accounts for how many bytes were written into the pipe, into the buffer, and it will internally keep this counter 12. And when this guy tries to read it, it says, okay, if it tries to read more than 12 at once, then it will just return the content of this buffer, hello, and so on, world. and will return here as a result, will return 12, saying, okay, you read 12 characters. Do whatever you want with it. It might be a string, it might be a binary object, whatever. It doesn't care, right? But it will drop this counter to 0. And if you're trying to read this size, like, for example, less than 12, so let's say 7, it will read you 7 because 12 are available, and it will remember that 5 more characters is still, or 5 more bytes are still in the buffer. And if you come back again and read again, it will return you 5. And after that, next time you read it will return you 0. And at this point, you know that, okay, I'm done. I'm done reading the pipe. Does it answer the question?
Yep.
Okay. It doesn't know about the string. So we kind of like caught this interface, just cuts this. There is this semantic gap. It doesn't know what it has in a pipe.
I see.
Okay, other questions. Is this convention always pipe 0 read and pipe 1 right hand of the pipe? Right. So this is the convention. And if you go to the really quickly switch here to the main page of pipe. Sorry, here it's not really like how do we use -k pipe? It will just list all the pages, all the main pages which contain description for pipe. So it's either a, and I didn't program for so long, so I have to put 2 here. No, that's like for the, so what else here? Main -k2. Nice. That's scary. I don't remember how. No, really? How do I read the specific main version? I don't remember anymore. This is kind of okay. Man. I just wanted to like page pipe. How do we read a specific version of a page? Man2 stat. Okay, cool. Man2 pipe. Okay. Oh, so this is like this is specifically a main page which explains how pipe can be invoked from C. So like you use this file, it says, okay, you pass an array of 2 integers, right? This is the syntax in C. And if you carefully read it here, so yeah, like essentially it will explain the convention that one of them is a read end of a pipe and 0 is a write end of a pipe. Make sense, Robert? Okay, so and the reason I'm showing those main pages is that Applejet, you can always do something like you say, look, I have no idea how pipe works, and I say something like pipe Linux C just to make sure. Okay, example, to make sure that we can invoke pipe and from C. And I do the same most of the time. I use Google or something to say that, okay, I have no idea how to invoke this interface. So I will try to make sure that I will read it, right? But you can as well do something like man2 pipe. And sometimes it's quicker. If you're already familiar, it's like back in the days, that was Google. So we didn't have internet, right? So those man pages were your manuals, which you had on your machine. Now you have it. So either works. Any questions? Joseph, so like maybe if you joined later, so the class will be recorded. We are still finishing the lecture from Tuesday, and so we're talking about the code, this one, which essentially allows you to connect whatever program you're running to a WC, right? And it's not very hard, so you will be able to essentially watch through the lecture which I'm recording and man2 pipe. Oh, yeah, Carson, thank you. So yeah, sorry. Okay, got it. So we can move on, right? Any other questions about the pipes? I apologize. Where is my, like, this is the slide deck. Where is the slide deck? Okay, good. Pipes are good. Any questions? Okay, so we just saw an example which allows us to use those two system calls, fork and exec. The code looked like this. Let me erase everything. Oh, and really, erase all like you see that you can do a fork. Sorry, you can do a fork, and then you have a window of time here which allows you to do something with file descriptors, and then execute exec, switching the address space of the program, essentially starting execution of the main function of WC at this point. And whatever you do here in this window of time allows you to manipulate the file descriptors. As I was saying last time, it was nice. It lived for like 50 years, right? So they came up with convention. Everyone was happy for a while. But if you were to design an operating system today, again, one more time, sometimes this interface of a fork and exec is not ideal, and you want something like spawn or something like a create process, and which takes like an argument bin WC, and maybe you say, look, please, here is an array, and like whatever, some kind of a mask. If you say one, the file descriptor is passed from the parent to a child. If it's 0, it's not, or some kind of a convention here to specify which file descriptors you want to pass into your child, right? So you can kind of, or maybe you need 2 arrays because really like, because you want to pass this file descriptor, which is like, I don't know, open 6 has to show up at position 0, right? So you want something like 6 right here. And maybe here it's an whatever, an option type says none, and making sure that nothing will be opened in a child. And the reason you want to avoid doing this fork and exec is not entirely like immediately transparent, right? But what the fork does, like essentially, if you have a parent, it just creates a complete copy of a parent, P2, which the moment you execute exec into WC, you kind of throw away. You just say, okay, whatever was here, I'll just dump it. And this has to become WC, right, from now on. First of all, unless you carefully implement this, and there are ways to make sure this like this copy is optimized as hell. Like it can be like copy on write, meaning that you never really copy the pages, but just more like have pointers to the pages of a parent, and only when parent or child try to write into these pages, you try to copy. Or like there are variants of this exec system, like fork and exec, which immediately execs. But the problem is that it still kind of assumes that you can do this trick. And it's hard to kind of explain, but imagine this process runs in a language like Rust. It's not C. We will talk about page tables and like how this process address spaces are built. But if you're running in Rust on some embedded device, you may not even have the page table, like which I didn't explain obviously yet. And then doing this fork, this clone of a process is very, very tricky. And so you might want a choice that, okay, forget about it, it's too hard. And specifically, as I was saying last time, I did this choice multiple times with my students. We like typically the operating systems which we built, they don't really have fork. They emulate fork later on. So it looks like it's a fork, but really in most cases, we never finished the implementation, honestly. So it just doesn't matter. Okay, so to some degree, maybe it's not ideal, right? But it lived for 50 years and people are happy or people are unhappy, but essentially in environments where this cloning of the address space is hard, and specifically like Amazon, I will use Amazon Lambda. It's just any serverless environment where you say, look, I run some tiny program, I want to clone it. It becomes hard in some cases, but it's hard to explain right now. We'll get to it hopefully later. Okay, any questions about fork and exec? All good? Man, with this speed, we'll never finish this lecture. Okay, so a little bit more system calls. So, like not surprising, when you want to terminate the process, you call exit. And at this point, the process exits in the operating system with a system call, which is exit and never returns. And at some point, the operating system just cleans up all the resources, like the address space of the process, and says, okay, like, it's gone. So wait is another system call which allows the parent can wait for a child. So essentially, like, the operating system will like maintain a hierarchy of children for you. And essentially, when this one is exit, this is the child. And if the parent is waiting and this child has a PID of, I don't know, 77, this wait will return 77 as a process ID, because maybe this 88 is still running and you can distinguish them, right? But you can wait for them, right? And you'll have to use it in your shell to make sure that children finish before you essentially print the next command prompt on the screen, right? A couple of obvious system calls like make directory, which creates a directory. So essentially we say, look, everything starts from a root directory, which is a slash, and maybe you have a bin, you have whatever. What else do you have? Home, anything, right? Inside home, you have enter. And so this mkdir allows you to create those directories. Open allows you to essentially create files, or if you like, you can open an existing file, obviously, or you can open with this flag create, which creates a new file. mknode creates an empty file, which will be marked as a device. And that's the way to connect, kind of like you can write something into a file descriptor, and really it doesn't go into a file in a file system, but will go to something like a device driver, which is console, for example, like keyboard or or serial line or VGA screen, right? So we'll see how x86 does it. fstat allows you to retrieve information about the file. So we'll talk all about it. Link creates a link to a file. Unlink deletes a file. So for example, on the Unix, it's possible to open a file. So essentially, like, this is how you can create a temporary file in a TMP folder. You say, create a file with a new name, XYZ. I create it for reading and writing, and then you unlink it, right? It doesn't delete a file because this file descriptor still points to a file, but unlink kind of removes it from a file system. And the moment you do close on this file descriptor, this file will be like essentially deleted in a file system. Okay, a couple of questions. Can you wait for a specific child if there are multiple? No, not in the x86 interface. And I don't think POSIX supports it, although I'm not like a big kind of like, I don't have an encyclopedic knowledge about POSIX. So I don't think yes. So Griffin says, yes, it's possible. Okay, cool. Griffin knows more than I do. That's cool. Proud of you guys. So yeah, I didn't know, but cool. So not in x86. I think x86 only will implement one wait, and it will just, whoever exits will get a, like, you will get a PID of that process from a wait function. How does a child get assigned a PID other than 0? So PIDs are, again, it's not an ideal mechanism, but essentially a operating system just says, okay, I have a list of processes. Now, as I think about it, it tries to assign them sequentially. So if you do something like PS minus all processes in the system, right? And no user X. Not okay. This. So on my machine, those are the PIDs, right? So if I grab for 0, a big grab. Really? My goal was to essentially make sure that I will see PID 0, but why? Like, okay, grab for init. I wanted to see init. So on Mac there is no init. What do we do? On Linux there is init. So like, let's quickly do SSH into a BSD system. just to show you PS UX wrap init. Sorry. So as bin init is the very first process which is created by Unix system. So which like leaves for as long as system is running. So it's probably not the case on Mac OS. And so it's get assigned a PID, right? And if you say, look, show me all the process identifiers, so like you will see that they are increasing. So this column, right? So essentially this PS command lists all the processes in the system. Again, this is a useful example of using this power of the shell and combining small little tools. Like here I can see what's running. So there's like kernel daemons, stuff like that. So it's kernel threads in those vertical brackets, in square brackets, sorry. So, but so supposedly PIDs are monotonically increasing. And I would imagine it shouldn't loop, but maybe you can essentially like make sure that at some point you loop. I don't think it matters that much. I don't know whether that was your question, but essentially, like, you know, like this BSD time runs for how many, like 176 days, right? So a fair amount of processes are created, right? So I think they are monotonically increasing typically, but you can come up with a different way of assigning PIDs. As long as they are unique, you can uniquely identify a process, and that's enough for this interface. Because when you do something like kill some PID here, then it will kill this specific process. Okay, so any other questions? Oh, good. Okay, so one interesting kind of high-level observation is that, and which is the beauty of this interface, that all these system calls of x86, and these are all of them, fit on one screen. That's pretty amazing. It's pretty amazing that when you create a system call, when you create an interface, which doesn't require like thousands of pages of explanation, but really fits on a screen. So everything what we covered in this class is so far, and everything what x86 implements, and we'll kind of boot an x86 maybe like in a couple of weeks or something, will be here, right? So essentially you can quickly say, look, can I do something? And yes, here's an answer. And so that's the power of this interface. That's, you know, like, what's the beauty? The beauty is that if I am to evolve x86, so for example, I want to provide a backward compatible x86 kernel on my Android device or something like that, supposedly the only thing I have to do is implement those system calls, and then supposedly stuff will be running, right? So the smaller number of those system calls you have, the easier it's to like move forward. If you have 200 something system calls, then you have to implement each of them or you break compatibility, right? And well, that happens in real life. So the smaller the interface is, usually the easier it's to leave and optimize and implement. But finally, how I wanted to end this lecture is I wanted to say that in many ways, this x86 is very similar to the operating system we're running today. So like FreeBSD, in which I was just recently SSHing, right? Mac OS. This is the tree of those dependencies. Let me just real quick kind of like show you here. So we're talking about Unix version 6. So that's this one. There was later like Unix version 7 here, and we forked into BSD. It was proprietary. We later forked into FreeBSD here, right? And FreeBSD is still alive. Linux supposedly never really forked the code, but you can probably say it was inspired. So this is like an inspiration link between these two. And like Linus Torvalds started from scratch, but you know, like inspiration was still the same interface. And if you like, if you look at, you say, look, these are all exotic systems. I don't really care about them. Another version of this plot is that from this Unix, which is version 10.5 probably, you like, this is the inspiration for Linux, but I wanted to show Mac OS. So there is a link here between the Mac OS, which I'm running right now on my laptop, right? So through a Berkeley BSD version, But in practice, what's happening here, not exactly sure why we're calling this next step, but essentially macOS runs a version of a BSD kernel as part of its architecture, right? So essentially, like everything was like macOS is a very powerful GUI on top of like a tiny microkernel XNU, which runs free BSD, and BSD is a free version of BSD, and on top of it there is a Mac. So, and like XNU and FreeBSD are open source. So if you like go online, you can download the source code and see how it works. But the GUI, of course, is proprietary. So the open part is, I think, Darwin, and that's an open version, and macOS is a closed version. So essentially, my point here is that we started here in the 70s. We are now in 2020s, but like there is still a very strong connection between x86 and other Unix kernels, and like production quality desktop and server kernels we're running, right? So like Linux is a de facto standard kernel in a data center. And finally, what I wanted to say is that this is a picture from one of the Unix conferences, and the reason I'm showing it, that's because it was happening in Salt Lake City. So, and like there's a bunch of famous people here, so you can look it up on the wiki page to see who is who. But the point is that like University of Utah and this community was always kind of connected to the development of all those kernels. And for example, one final kind of an anecdotal interesting fact is that there's a person here who sits in the Maryland Engineering building who was working on essentially implementing this fork, so specifically this line, so making sure that BSD is free from this proprietary software. Person's name is Mike Hibler, and he's a great kernel hacker. And like if you grab through the source code of XNU kernel or whatever the version macOS is running, you will see his name there. So essentially, his code is still running on supposedly my macOS, and it's a code which implements virtual memory management. So like virtual memory. It's pretty impressive, and how like something what people around you are doing, and then you see them like running for decades. Okay, so this is it. So with this lecture, any questions about the operating system interfaces? So the reason we covered it, so let me just wrap it up. So the reason we were talking about operating system interfaces is that, remember, if you have a kernel which you built, let's imagine x86, the interface which it exposes, like this fork, exec, or maybe it's a different kernel, maybe it's a Linux, which you can run on Kate. Essentially, when you run a process, that's the interface the process can use to do something on a kernel. You can create other processes, open files, stuff like that, right? And our homework assignment will be to essentially build a simple version of this cell. So essentially the program which parses the string, the command prompt, implement pipes, implements IO redirection. And some of you already did it. So, and like you're welcome to reuse your code base, or welcome to build from scratch, because probably we'll be asking for a smaller subset of features. But essentially that's our first homework assignment, which we'll try to assign today or tomorrow, realistically. Okay, so we understood what this interface is. Our lineup. Okay, the question is like, do we have to learn anything else? Or maybe, maybe it's enough. We like, why would you really try to learn anything about operating systems? So the way the class is structured, our main focus will be kernel. So we will try to, like, we know how the interface should look like. Until the rest of this class, until whatever, April, we will be looking at how those system calls are implemented. We'll take a look at how we're going to boot into the kernel, how we will get to main, how we can set up like kind of enumerate all resources like available memory, stuff like that, create a tiny virtual memory allocator. We'll start building new processes, essentially, like we'll start a first init process. Init will obviously, there will be some kind of like init will fork and we'll start a shell, exec into shell, shell will be running. So we will essentially, our focus will be looking into how you implement this kernel. That's the whole class, right? So after that, supposedly, if someone asks you, okay, if you execute this printf line, hello world, like in your program, imagine it's a job interview. What happens? Can you explain what really happens next? And you say, look, well, printf is a library function, but really what it does, it's probably writing in a file descriptor, and most likely in a file descriptor one, unless they like explicitly provide a file descriptor like number here, and it drops into the kernel and it prints file descriptor one, points to the console connects to the VGA screen or to something else. And essentially that's the understanding we're like thriving to achieve by the end of this class, right? So we'll gradually, it will take me some time to explain every bit of this kernel, but by the end of it, you will be able to say, look, I understand how it works. Like I know when machine runs, in fact, I can maybe even guess the next instruction, like the very first instruction inside the printf function. And you will be able to make an educated guess, and you can be wrong because there might be some additional assumptions about what's inside this function, but you will be pretty close. And that's pretty amazing because you will impress anyone who will interview you with this in-depth knowledge, right? But before even getting to the details of what's running inside the kernel, we kind of need to understand what will be running inside the process. We really need to understand what the process is. So essentially, remember, you start from a file, like a C file, where you have like whatever, main.c. You take a compiler, like a GNU C compiler or whatever, LLVM. You compile into an object file, main.o. Then, you link it and you say, look, I got the whatever, the name of this program, but let's say it's a main. But at this point, it's an ELF file and it's linked maybe with system libraries, or maybe it's not linked, but will depend on shared libraries, right? This ELF sits in a file system. And so when we do exec of this file, exec will load this file and like essentially load the main here inside the process, start running. So our next couple of lectures will spend looking at what's inside the process. Because remember, I was trying to kind of like explain this vision before. I said, okay, no matter what I'm saying about operating system, no matter what the book is saying, the very first goal, like its pragmatic goal, is you simply need to run programs. Like you can make a very simple kernel. You can say, look, I don't support exec, I don't support fork. I simply run one program, one main function, like Adrena does, and it will read like sensors and will be happy and will be like doing my wearable device, right? And that's essentially a detour to understand what's inside the process. And to do that, we first look at what assembly instructions are, like how machine executes the code. Then we talk about the calling convention, like how you invoke essentially like execution environment inside this process, like how you set up a stack, how you call a function, how you return from a function. Then we talk about the L files. Then we essentially figure out what the process is, and then we will go and start looking at how the operating system kernel works. So that's essentially the overview of what's coming in the next, I would say it will take us a month. So almost until the midterm, we'll be looking at this, because it's just all these details are important. But again, like my goal is to make sure that to get this level of understanding, someone says, okay, here's a line in your code. Do you know what's going on? And you can say, like, yes, I know what the kernel is doing. I know what the execution environment inside the process is doing and stuff like that. So it will take us some time. Okay, any questions about it? All good? Then I will, like, I know it's a little hard. So we've been here for almost an hour, but let me start the next lecture. So it's relatively easy. So nothing super like, oh, go ahead. I forgot, didn't catch it. So someone was asking a question. Okay, our today's lecture, which will probably run for at least a couple more lectures because we started this one late. I don't know why I spent so much time. Wanted to talk about pipes and everything. But essentially, what we're doing right now is we're talking about x86. I will give a brief introduction to x86 assembly. Like essentially, the goal here is to understand how machine works, right? It's how it executes instruction by instruction. And how you need to what do you need to do to get the process running, right? So that's the ultimate goal, right? Okay, I'm pretty sure that there are people who already kind of reasonably well familiar with this material, right? So still kind of not teaching it at all will be kind of a crime probably, because I like everyone to understand everything. I'll try to move faster just to make sure that we kind of don't waste too much speed on this. But so bear with me for a second. Okay, the very first thing is that how do the CPU works? How do the CPUs work internally? And I talked about it before. So essentially I said, okay, guys, we all understand that CPUs are essentially execute this fetch, decode, register read maybe, and execute loop. And what happens here is that, there's a special register on 64-bit machines. It's called RIP. Alternative names are instruction pointer or program counter on MIPS, right? So it's all the same. But the point here is that this register, contains a value, which is an address. And this address is the address of the instruction which the machine will execute. So if this is memory, essentially, the CPU will say, okay, it will generate the instruction pointer because maybe the previous instruction changed it. Maybe we called a function, maybe we jumped. Maybe, we jump to a page which is not mapped, and it will trigger an exception. If it didn't happen, well, essentially the CPU, and that's the logic of a pipeline, will just read this memory location. On Intel instructions of variable lengths, so Intel probably reads enough to make sure that it can decode the entire instruction. On something like MIPS, which we covered in 3810, all instructions are the same size, so you just read 4 bytes or whatever the size of the instruction is. The CPU logic decodes this instruction, essentially looks at whatever bits are here. It's an addition which does read 2 registers, whatever the instruction format I came up with was 3 register, which is like a made up instruction format. It doesn't exist on Intel. But essentially, it can read these 2 registers and maybe add those RAX and RBX and put the result into RDX, right? And essentially read the registers, run through the LEU cycle. If we didn't have a fault, addition, I don't think addition can cause a fault, or maybe it can cause a fault if you configure the system to fault on the overflow. You're adding 2 large numbers, they just don't fit into 32-bit representation, for example. You commit the instruction and you essentially say, okay, at this point, did we update the instruction pointer? Well, if no, we increment the instruction pointer by the size of the current instruction. So essentially, if this is some size, like 5 bytes, we say, okay, RRP will be RRP plus 5, right? And we will repeat this loop again, reading this new instruction, stuff like that, right? Not very hard. So kind of all machines work this way. Of course, there are lots of different interesting details in the pipeline. Everything is out of order. There are multiple execution units. For that, you need to take Rajiv's hardware architecture class. He's a very good teacher. He will explain you everything. So it's totally worth it, right? Or even watch through his videos. But again, for our purposes, we kind of have this simple model and it's good enough. And now the question is which we're trying to answer it in the next couple of lectures. What are those instructions? So essentially, I will provide a brief introduction to the x86 instruction set. The reason I'm doing it because we will, in order to even construct a process, you have to construct an execution environment. So the process will not run unless you set up a stack correctly, because the main function will call something or allocate local variables on a stack, and immediately, if you don't have a stack, it will crash, right? So, and if you're running some other more complicated language like Java or maybe Rust, Rust has thin runtime, but Java has a thick one. You might have to set up even more, but in the end, it's kind of the same. So you set up this execution environment, and C is good because it's so transparent. It compiles almost to assembly. We'll take a look at the disassembly of the code which our compilers generate, and we'll see, okay, okay, got it. We understand that whatever we learn in this lecture is really what's inside the program. That's again will confirm that our understanding of what's going on is correct. Okay, a couple of notes here. So in this class, we'll be talking about the 32-bit version of x86 instruction set. It's a little bit dated, right? Because right now we're running 64-bit of everything, 64-bit versions of everything. However, the version of x86 which we're using in this class is still a 32-bit operating system. And you're welcome to take, oh man, really? You're welcome to take a look at the 64-bit port, but really, it's interesting, but there is nothing like inherently different about it. So if you understand how 32-bit machine works, 64-bit machine is a tiny little step forward. And we do have a port. We did port the x86, but all the books which MIT guys wrote, they're still written about 32-bit versions, and we never really updated the books, right? Okay, that's why 32-bit versions. By the way, MIT people now looking at the most recent version, they switched to RISC. So they said, okay, it was all nice, but we don't want to teach x86 anymore, and we're going to be, they rewrote x86 and they use a RISC version of the kernel. I chose not to do it, RISC-V, just because I believe that if we work with x86 instruction set, it gives you a little bit more concrete knowledge, which you can like essentially go tomorrow in a data center. And in a data center, the chances will be that you're running x86 machine or maybe an ARM machine, right? So, and I chose x86. That's fine. Then you say, look, I understand how it works. I really in-depth understand how x86 machine works. So hire me, I will do whatever is needed. I understand how it can get exploited. I understand how to optimize it, right? So I have this knowledge of like x86 execution environment, right? That's why x86. So any instruction set of a modern computer is reasonably complicated. There are like tons of extensions, and like it's kind of hard to understand how it works. But the very core of all of these machines is very, very simple. So it's somewhat similar to a MIPS machine, which you did in like 3810 class, right? So at a high level, there are three main groups of instructions, right? Instructions which load and store or move something in memory or in memory and registers. There will be arithmetic operations which allow you to add, divide, multiply, something like that. And there will be control flow instructions which allow you to execute jumps, function calls, return, stuff like that, right? So we quickly cover all three and just understand how they work. On x86, again, 32-bit version, each register is 32 bits long, and there are only 8 general registers. There are some very nice blog posts online which try to count the total number of x86 registers, and you will be pushing something like 200 registers. Wow, I said that, okay, the thing is complex, but the core of it is very simple. Just 8 registers, and we're going to be talking about those 8. Some of them have names like EAX, EBX, ECX, EDX, ESI, EDI, ESP, EBP. And these two registers, a stack pointer and a base pointer, they have kind of like a special purpose. So I will explain. Stack always points to the current position of the stack in memory, and base pointer register points to the frame in a function. We don't really need to support it always, but like it's always supported, right? So which like leaves you really in x86, it leaves you only with 6 registers, right? So not much, right? But those general purpose register, they can kind of participate in any of the arithmetic instructions. Those two can also, right? You can change a stack pointer, you can change the base pointer. So you can do, but typically they're taken because compiler says, okay, they have a special meaning in my program. If you want to call functions, then the stack pointer should point to the current stack location. Otherwise, you will fail to either call or return from a function. Like once in a while, like if it's an in-class lecture and I'm in person, I will ask people what these registers are. Like really, where are they? Like, are they here in memory? Are they here on a core? And people are sometimes confused, right? So, but this is a pipeline, a 5-stage pipeline from a simple MIPS system or whatever it is, like 3810. And typically, this pipeline obviously is implemented by one of the cores. Like here we have a CPU with 4 cores on this diagram. And this is like an implementation of a simple but like reasonable pipeline. And this is the register file, right? Remember I was saying it has multiple stages: instruction fetch, we read instruction, we use a program counter, read instruction from memory. The result of it is stored into intermediate register, which is called a latch. Then we like decode the instruction, see what needs to happen to this instruction. And sometimes we read this register file and put it like in some intermediate latch registers here. And if we do addition, we use this arithmetic logical unit to form an addition and maybe like write back to the register, stuff like that, right? And here we just generate next program counter. So on Intel EX, like they live here. I just wanted to make sure that we understand that those are the guys which live like it's they implemented in silicon, they live like and participate in the execution of the pipeline, right? To be accessed in this one cycle. So it's instruction decode and register fetch immediately in a single cycle. So got it. So that's not super surprising. Again, everyone probably by now everyone probably knows it. So any questions about it? Okay, we get the registers. The first instructions, the ones which move data between memory and registers on Intel, we'll use the following connotation, right? So if we say register 32, we mean any 32-bit register. So essentially any register, sorry, wow, click something on my pen. Any register from this set. If we say any 16-bit register, it's like a subset of registers which have like 16-bit names, similar for 8-bit registers. If we say memory, then it will mean like a memory location or memory address. If we say a constant, we mean a constant. And the way instructions are written, so for example, this is a move instruction which copies the data referred by the second operand into the first operand. And so we say immediately, and we'll see the same format for any instruction which we will be discussing. It's a look, I will, whatever the register here, I will copy the data from this register into this register. And these are all possible combinations here. So you say, look, you can copy from memory into register, you can copy from register into memory. So this is kind of a load operation. This is a store operation. You can load a constant into a register, or you can save a constant into memory, right? Not surprising. So that's the move instruction. The surprising part is that on Intel, they don't have explicit load and store instructions. Instead, they use moves with different operands, right? Okay, so a couple of examples here. So like in this like lecture, we use Intel syntax. This is a little crazy. So over the years, there are 2 major syntaxes like Intel and AT&T. I'll cover the difference between them. The major difference is that the way we write operands on AT&T 6, like it will be, this instruction would be written something like EBX into EAX. So we kind of flip the direction. Sometimes it gets really confusing, but sometimes you can guess from the context what's going on. So on Intel, we're reading from register EBX here, writing into register EAX. Here we're saving constant 5 into a byte location because we specify that this address pointed by the var variable, but we only will be saving a byte because 5 fits in a byte. If you don't say a byte here, then like the instruction will happily like take the word and essentially put 5 here, and those will be zeros, right? But this variant will not essentially override the other bytes. So essentially, whatever the bytes here, where we only update 1 byte here, right? So here, move 4 bytes. So by default, you use 4 here in memory, from memory pointed by the address contained in EBX into the EAX register. So this is a load. Here we doing a store. We are like using a constant address here, whatever was in the EBX register, we're saving into memory pointed by this under address with value variable. So Intel allows you to do a tiny computation on registers. You can do like ESI -4. You can also add 2 registers, ESI plus ESX. as we see on the next slide, it helps you to essentially like access data structures and stuff like that. So for example, if you have a data structure, which is a point, which has two fields, X and Y, both of them like 4 bytes, and you have an array of those points, right? So essentially, if you want to load the Y's coordinate from the I's member of this array, so essentially you have an array, here's an I's member. This guy will have obviously 2 bytes, which is X and Y. And you say like, from the points array, I want to load this, which is sits here, right? This location. In assembly, the way the compiler compiles it, you say, if EBX is an address of the points array, each element of the array is 8 bytes because it's 2 by 4. So I sits inside the EX register. So, and of course, since we want to access Y field, it's +4. This is the arithmetic. You say EBX plus 8, EX plus 4, right? Got it? So that's, and you load it in the EBX register. Agree? So that's the reason why I invented this reasonably complex instruction set. They thought, okay, majority of the times you access some complicated, complex data structures with multiple fields. So we will allow multiplication here, and we will allow to use a base, index, and some offset to essentially access those data structures, right? Okay, cool. Similar but slightly different instruction, load effective address. It's better to understand through an example. So if move really loads the value into the local variable Y here, load effective address kind of takes the address of Y, right? So in this diagram, it says, okay, I want to know the address of this element Y. So you use this ampersand and C, and I want this address to be saved in a pointer, which is P here, right? That's how you define a pointer, declare a pointer in C. Then you use this load effective address instruction. So essentially, it will not touch the data. It will run the same computation because the address of this field, like points I and field Y, is same as, the only difference is this ampersand. But instead of like loading the data, you just save the address into this ESI. So you computed this pointer, for example, right? So move and load effective address. Load effective address is often abused by the compiler because the compiler says, okay, by the way, I can use load effective address to do some funky arithmetic operations. Like I, for example, can like compute the values of EX plus EBX plus some constant. Or I can like, essentially it allows you to compute 3 operands. Or you can, for example, a typical addition instruction will overwrite one of the arguments, right? Because it will place the result in the first argument, right? But load effective address says, okay, I have 2 different registers. I'm not going to lose the values in them. I will add them and place the value in the 3rd register. And there are some funky multiplication rules which you can do with load effective address. So the reason I'm explaining is when we start disassembling this code of real like utilities, which we'll see on Linux and in x86, sometimes you see a load effective address, but there are no arrays, no point data structures like here. It just the compiler abuses this instruction to do some computation. So it's not uncommon to see it in disassembly. Not super frequent, but still happens once in a while. Okay, cool. We can load data from memory into register, stuff like that, right? The next set of instructions allow you to compute something on memory and registers, right? So addition, for example, adds together, sorry, 2 operands, storing the result in the first operand. So it will be like whatever, 2 registers plus store in the first one, right? And same, you can use memory, store in memory, you can use a constant, you can save something in memory. Like, let's take a look at some examples. So if you had addition EAX 10, it will do EAX plus 10 and essentially place the value back into the EAX. Here I say I will take var points to memory, right? There is a byte at this location of var. Maybe this byte is 77. I will add 10 plus to this 77 and we'll store back 87 into this memory location, right? So this is what's written here. Again, not super surprising. I I want to go fast through this just to make sure that you know, we guys can quickly finish this lecture. Similar subtraction, you know, you take two registers, 1 minus second, result goes in the first one. So here we subtract 216 from the value inside the EX register. Again, nothing super interesting. They have explicit versions of increment and decrement instructions, right? And oh, cool, yeah, it's yeah, nothing like surprising. Instructions for like bitmask operations. I don't know how well you are familiar with bitmaps, but and why they are useful. But often, like, you use those to like check specific or shape specific values of like control registers. We'll see how x86 uses those. So like they have AND, XOR, and all the like all typical bitwise separations, right? So again, shift left, shift right. Not surprising. By the way, all the instructions which I covered here, I will link from the class website. I will link a document which talks about essentially each of those. They're like, it will be an assigned reading, so you will have to read through those. But I'm just giving an overview. More instructions. So you have integer multiplication. You will have division, bitwise logical NOT, negation, like essentially everything what you want to like you will not be surprised. So x86 has everything what you want, and some exotic instructions as well. So if we quickly kind of like move through this set of arithmetic operations, essentially we have moves, we have additions, we have whatever increments, we have moves again. So we can load something from memory into a register. We can save something from register into memory, right? So you can write a fair amount of programs. But if I ask you a question, so the only question which I have to ask, which I can ask today, what are we missing? So essentially, those instructions are good. They provide enough material to like write meaningful programs, but something is missing. So what is missing? Which programs you will not be able to write? Okay, Ali?
It could be if else can do this. Conditional statements.
Yeah, conditional statements like if a equals to 0, then do then statement, else do something else, right? So how do compilers generate this code? Do you guys know? They use, okay, anyone knows how to do it? Okay, someone has here. Jump instructions, correct. So this will be a comparison. You compare, let's say, A inside the EX register, compare with 0. On Intel, you use a specific flag register, which stores the results of comparison, but then you can say jump when equal. And if EX really equals to 0, you, for example, jump to then part of the code, right? It's kind of like inverted. So this one gets compiled here. You can compile it differently, right? You can like negate the expression, stuff like that. If it's not equals to the 0, you continue executing the else part of the code. But of course, since you don't want to execute to remember my story about instruction pointer, which keeps incrementing, you don't want to execute then part of the code after else. So here you will have an unconditional jump to a label, which is somewhere here, right? After all of this code is done. So you will jump to something like this A line, which essentially implements the next line after the if then else statement, right? So for that, as Ollie said, we need two primitives. You want to compare and you want to jump conditionally, right? Similarly, like if I want to implement a loop, we will be comparing for some condition in a loop, right? I is greater, what is it, less than 0. I is greater than 0, for example. We can decrement I, and essentially there will be like code, there will be some kind of a comparison. there will be some kind of jump when greater, and you will be jumping to the beginning of a loop. So essentially, this is how compilers generate this code. And we'll take a look at the disassembly of like simple programs to just confirm our understanding of how essentially it works, right? So you essentially in this, like if you have arithmetic operations, everything is fine, but you can't really build those programs which have loops or conditional statements. You can, but I don't want to go into the details. It's called conditional. You can use conditional move instructions, but if I go into those details, you probably will hate me forever. But it's a nice, interesting research topic. Let's not go there for a second. Okay, so boy, man, I have a poll. Probably not a good time for a poll today. So since everyone is on Zoom, we'll skip over the poll real quick and we'll maybe return to it like next time. But the next group of instructions are those control flow instructions. I just wanted to make sure. So probably, since we only have 2 minutes left, I should probably stop here and essentially start the next lecture, hopefully in person on Tuesday, by coming back to those control flow instructions and essentially explaining how we implement if-then-else statements, and then how we implement function or procedure calls, essentially function invocations and returns, and how the stack is involved, how arguments are passed. And so we will spend a lecture, at least a lecture, on calling conventions, essentially on how to call functions and stuff. So, okay, let me stop here. Any questions right now? Okay, I appreciate that everyone was willing to attend on Zoom today. Thank you so much. I'll see you then on Tuesday. Have a good weekend.